Our universe is hiding a secret motion on a scale you cannot fathom. Galaxies by the thousands are streaming in a direction that makes no sense, pulled by a force from a place we cannot see. This is the mystery of dark flow, one of the greatest cosmic puzzles of our time. By the end of this journey, you will know 50 staggering facts that could rewrite our story of the cosmos. We will explore what could be tugging at the fabric of reality itself and ask if everything we know about the universe is wrong. What do you believe is truly out there beyond the edge of everything we see? The first clue arrived in 2008, not from peering at stars, but from listening to the faintest whisper in the cosmos. A team of scientists led by Alexander Kashlinsky was meticulously studying data from a remarkable satellite called the Wilkinson Microwave Anisotropy Probe. This satellite was designed to map the cosmic microwave background, the afterglow of the Big Bang itself, a nearly uniform sea of ancient light bathing the entire universe. Their work was painstaking, like trying to hear a single instrument tuning in a vast, distant orchestra. They were looking for tiny, expected ripples in that background, the seeds of all future galaxies. But they found something else entirely, something that should not have been there. Buried within the data was a powerful signal, a kind of cosmic Doppler shift affecting not just a few galaxies, but hundreds of massive galaxy clusters. It indicated these colossal structures were all moving together in a coherent stream at a staggering speed of over 2 million miles per hour. This was not a gentle drift. It was a violent, coordinated rush. The scientific community was stunned. The prevailing model of the universe had no room for such a motion. According to our best understanding, the universe expands uniformly in all directions, with galaxies carried along like raisins in a rising loaf of bread. There should be no preferred direction, no grand current on such an immense scale. Yet the data screamed otherwise. It suggested that something unimaginably vast and powerful, lying far beyond the edge of everything we can see, was exerting a gravitational pull on the entire observable cosmos. This was not just a new discovery, it was the first crack in the foundation of modern cosmology. This motion defies every local explanation. It is not our Milky Way simply sailing through its neighborhood, nor is it our entire local group of galaxies drifting together. Those are small, understandable currents within a much wider cosmic sea. Dark flow is the sea itself moving as one. We are talking about a coordinated stream of thousands of the most massive structures in existence, galaxy clusters, each containing hundreds or even thousands of galaxies like our own. These titanic islands of stars and dark matter, spread across unimaginable distances of up to 3 billion light-years, are all being pulled in the same specific direction. To grasp this scale, picture a single light year. The distance light travels in 1 year, which is about 6 trillion miles. Now multiply that by 3 billion. Across that mind-numbing volume of space, the random, churning motions of individual clusters should cancel each other out, creating a statistical stillness. Instead, the data reveals a silent, universal current. Imagine standing on a beach and seeing not just the nearby waves, but every wave for thousands of miles in every direction, all rolling steadily toward a single point on the horizon. That is the profound and unsettling coherence of dark flow. It suggests the source of this pull is not within our cosmic map, but far beyond its edges, a reminder that our entire observable universe might be just a small part of a reality we are only beginning to sense. The numbers behind this motion are what truly shatter expectations. These galaxy clusters are not drifting. They are being hurled through the cosmos at velocities between 600 and 1,000 kilometers every single second. To understand what that means, let us put it into a human scale. Our planet Earth orbits the Sun at a brisk 30 kilometers per second. Our entire solar system, in turn, sails around the center of the Milky Way at about 230 kilometers per second. These are the speeds that define our local celestial neighborhood. Dark flow operates on an entirely different level. The slowest clusters in this mysterious stream are moving at least twice as fast as our sun's galactic journey, and the fastest are rocketing along more than 4 times that speed. This is not a gentle tug, it is a relentless cosmic haul. Generating such incredible velocity across billions of light years demands a source of gravity so immense, so concentrated, that it challenges our very understanding of mass and structure. We are talking about a gravitational pull powerful enough to overcome the expansion of the universe itself, to orchestrate the motion of thousands of the heaviest objects we can see. What kind of entity could possibly wield that kind of influence from beyond the horizon of our observable reality? This coordinated rush has a specific destination. All that staggering motion is aimed like a cosmic arrow toward a particular patch of our southern sky, in the general direction of the constellations Centaurus and Hydra. If you could stand on Earth and point toward the source of this immense gravitational pull, your arm would extend toward that region of stars. It is not a precise bullseye, but a vast, deep space target. This consistency is one of the most compelling pieces of evidence for dark flow being real. Multiple independent studies, using different galaxy cluster samples and analysis techniques, have all pointed back toward this same general corridor of space. When separate lines of inquiry converge on the same unexpected answer, scientists pay very close attention. It means the signal is likely not an artifact of the data or a measurement error, but a genuine feature of the cosmos. Yet here lies the deeper twist, the element that transforms a puzzle into a profound mystery. Astronomers have scoured that region of the observable universe, looking for any known supercluster or concentration of mass powerful enough to be the culprit. They have found nothing. There is no known cosmic structure, no titanic assembly of galaxies and dark matter within our sight that possesses the gravitational might to command such a flow. The pull is coming from a place we cannot see, from beyond the map of our known reality. The arrow points insistently toward a blank spot on our chart, a silent, invisible attractor hiding in the darkness past the edge of everything. This discovery strikes at the heart of a century-old assumption about the cosmos. For generations, cosmology has been built upon a single, elegant rule known as the cosmological principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the matter in the cosmos is spread evenly, like the batter in a well-mixed cake. Isotropic means it looks the same in every direction you look, with no special center or edge. This principle is not just a nice idea, it is the very foundation upon which our equations for the Big Bang and cosmic expansion rest. It allows scientists to treat the universe as a smooth, predictable entity. Dark flow shatters that smoothness. A coordinated, directional rush of thousands of galaxy clusters is the very definition of anisotropy. It means the universe has a grain, a texture, a specific direction that is different from all others. It introduces a preferred axis on the grandest scale imaginable. If confirmed, this is not merely adding a new feature to our cosmic model. It is like discovering that the fundamental floor of your house is not level but tilted. Everything built upon it, our understanding of how the universe began, how it evolved, and what its ultimate fate may be, would need to be carefully re-examined. The philosophical weight is immense. It suggests our place in the cosmos might not be as ordinary or as central as the principle implies, hinting that we may be living in a special, moving part of a far grander and more uneven structure than we ever dared to believe. This leaves us with a crucial distinction, one that separates dark flow from the other great cosmic mysteries. It is not caused by dark energy or dark matter. We must untangle these shadowy terms. Dark energy is the name we give to the unknown force that is accelerating the expansion of the universe. It acts like a kind of anti-gravity, pushing space itself apart on the grandest scales. It creates motion, yes, but that motion is an outward rush in all directions, a uniform stretching of the cosmic fabric. Dark flow, in stark contrast, is a directional pull, a current within that expanding ocean. They are fundamentally different phenomena. Then there is dark matter, the invisible gravitational glue that holds galaxies and clusters together. Its influence is profound, but it is already woven into the calculations. When scientists measure the motion of these galaxy clusters, they account for the gravity of all the visible stars, gas, and the immense halos of dark matter surrounding them. The staggering speed of dark flow is what remains after all that local gravity is subtracted. It is an extra push, a surplus of momentum that cannot be explained by anything within the observable scene. Therefore, dark flow points to a source of gravity from beyond our cosmic horizon. It implies an influence from outside our observable universe, something entirely separate and even more enigmatic than the dark components we are already struggling to understand. We are not just mapping hidden forces within our cosmic home, we are detecting the shadow of a neighbor we did not know existed. The detection of this cosmic current relies on the most ancient light in existence. To measure the motion of galaxy clusters across such vast distances, scientists needed a fixed reference point, a stationary backdrop against which to gauge their speed. They found it in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. This radiation is the ultimate cosmic anchor, providing a universal rest frame. But how do you use this ancient light to track moving clusters? The answer lies in a subtle but powerful phenomenon called the Sunyaev-Zeldovich effect. Imagine the cosmic microwave background as a uniform, quiet hum filling the universe. Now picture a massive galaxy cluster drifting through space. These clusters are not empty, they are filled with incredibly hot gas, a searing plasma with temperatures in the millions of degrees. As the faint photons of the cosmic microwave background radiation pass through this superheated gas, they collide with the energetic electrons within it. These collisions give the ancient photons a slight energy boost, like a ping-pong ball being struck by a fast-moving paddle. This interaction leaves a distinct fingerprint on the cosmic microwave background, a tiny but measurable shadow or a slight brightening at specific wavelengths depending on the cluster's motion. It is a cosmic speed trap. By meticulously measuring these subtle distortions in the background radiation behind thousands of clusters, astronomers can calculate not just that the clusters are moving, but precisely how fast and in what direction they are traveling relative to the universal rest frame. This method is so sensitive it can detect motions imperceptible by any other means, transforming the cosmic microwave background from a static snapshot of the infant universe into a dynamic map of the present. It was through this precise, painstaking analysis of these imprints that the impossible current of dark flow first revealed itself. Such an extraordinary claim could not escape intense scrutiny. The announcement of dark flow in 2008 ignited a firestorm of debate within the cosmology community. Extraordinary claims, as the saying goes, require extraordinary evidence, and many leading scientists were deeply skeptical that the evidence presented was strong enough. The primary criticism centered on the data itself. Could this coordinated motion be a mere statistical illusion, a fluke arising from the way the galaxy clusters were selected or how the cosmic microwave background maps were processed? Critics argued that incomplete surveys of the sky or subtle errors in subtracting the light from our own Milky Way galaxy could create a false signal that mimicked a vast, coherent flow. Renowned cosmologists like David Spergel publicly challenged the findings, suggesting the team might have been fooled by systematic errors, the kind of tricky background noise that can plague even the most careful astronomical measurements. This was not dismissal, but a vital part of the scientific process. When a discovery threatens to overturn fundamental principles, the community responds with a barrage of rigorous tests, attempting to poke holes in the methodology and reproduce the results independently. This healthy skepticism is the engine of scientific progress, a necessary filter that separates genuine breakthroughs from measurement errors. For Alexander Kashlinsky and his team, the initial years were spent not in celebration, but in defending their analysis against a chorus of doubt, refining their techniques, and searching for more data to either confirm the impossible or reveal its mundane explanation. The controversy demanded a higher standard of proof, a verdict from a more powerful cosmic observer. That verdict arrived with the European Space Agency's Planck satellite, a technological marvel launched in 2009. Planck was the successor, designed with far greater sensitivity and resolution than any previous mission to map the cosmic microwave background. Its mission was to create the sharpest, most detailed baby picture of the universe ever taken, to see the faintest whispers of that ancient light with unprecedented clarity. For the researchers investigating dark flow, this was the moment of truth. Planck's superior data offered a chance to either confirm the mysterious current beyond any reasonable doubt or to expose it as a persistent ghost in the machine, a systematic error finally laid bare. The scientific world waited as teams around the globe began the painstaking task of analyzing the new maps, searching for the subtle imprints of moving galaxy clusters. The results, however, did not deliver a simple yes or no. Instead, they deepened the mystery. Some independent analyzers of the Planck data, using different methodologies and cluster samples, reported a clear confirmation of the coherent flow, finding the same directional pull toward Hydra and Centaurus. Other equally rigorous studies, however, failed to detect the signal with the same strength, or suggested it could be attributed to more complex local effects. This split decision from our most advanced instrument was both frustrating and electrifying. It meant dark flow was not easily dismissed as an error, but neither was it universally accepted as fact. The controversy was not resolved, it was upgraded. The question was no longer whether the initial data was flawed, but why the universe's clearest snapshot was giving different answers to different questions. This ongoing debate is the lifeblood of a cutting-edge mystery, proving that dark flow is not a forgotten anomaly, but a living, breathing puzzle at the very frontier of our understanding. The Great Attractor sounds like a cosmic villain worthy of such a mystery, but it is merely a local disturbance, located about 250 million light-years away in the direction of the constellation Centaurus. This region is indeed a gravitational sinkhole. Our own Milky Way, along with the entire local group and thousands of other galaxies, is slowly falling toward it, pulled by the immense collective mass of a supercluster of galaxies hidden behind the dusty plain of our own galaxy. For decades, its discovery solved a local puzzle about our motion. Yet when we place it beside the phenomenon of dark flow, its power fades into insignificance. The Great Attractor is a neighborhood pond, while dark flow is the tidal pull of an unseen ocean. The gravitational influence of the Great Attractor, as vast as it is, extends only for a few 100 million light-years. It orchestrates the motion of galaxies in our local cosmic vicinity. Dark flow, in stark contrast, commands galaxy clusters from distances up to 3 billion light-years away, far beyond the Great Attractor's reach. The speed and scale are incomparable. For the Great Attractor to generate the violent, coordinated rush of dark flow, it would need to possess a mass hundreds of times greater than anything we observe. We have mapped the region, peered through the galactic dust, and while we find a significant concentration of mass, it is simply not monstrous enough. This definitive mismatch forces a profound conclusion. The source of dark flow cannot be any known structure within our observable universe, not even the mightiest gravitational anomalies we have named. The true architect of this cosmic current must reside in the unseen, in a realm so massive and so distant that its shadow is the only evidence we have of its existence. This leads us to the most staggering implication of all. The source of this cosmic pull is not just hidden, it is fundamentally unreachable. It lies beyond what we call the cosmic horizon. To understand this, we must grasp a simple, profound limit. Our observable universe is a sphere centered on us, not because we are special, but because light has a finite speed. We can only see objects whose light has had time, since the Big Bang, to travel across space and reach our telescopes. That bubble of visibility, about 46 billion light-years in radius in every direction, is our entire cosmic stage. Everything we know, every star, galaxy, and mystery like dark matter, exists within this horizon. The gravitational source of dark flow, however, by all calculations, must be far outside it. Think of it like this: you are in a vast, foggy meadow. You can see a certain distance in every direction, and within your view, you notice all the tall reeds are leaning steadily toward one particular point in the fog. But that point itself is invisible, lost in the mist beyond your sight. That is our predicament. The force tugging at thousands of galaxy clusters is originating from a region of space-time that we cannot observe, because its light has not had time to reach us in the entire history of the universe. It is a ghostly hand reaching in from a place we can never see. This means the structure causing dark flow is not part of our universe's story in any conventional sense. It is a relic from a time before our cosmic horizon was set, or evidence of a reality that stretches far beyond our own. The possibility of a cosmic neighbor is not the only explanation for this ghostly pull. To find another, we must rewind time to the universe's very first moments. In the tiniest fraction of a second after the Big Bang, our entire cosmos is thought to have undergone a violent, exponential growth spurt called inflation. Space itself expanded faster than the speed of light, inflating a subatomic speck into a macroscopic universe in an instant. This theory elegantly explains why our universe looks so uniform on large scales. But what if that process was not perfectly smooth? Even the most powerful expansion might have had tiny wrinkles, quantum fluctuations stretched to colossal size. These imperfections would have created regions of slightly higher and lower density, like ripples frozen into the fabric of space-time. Normally, we think of these ripples as the seeds for galaxies and clusters within our observable universe. But inflation could have stretched some of those ripples to scales far, far larger than our cosmic horizon. Imagine blowing up a balloon with a faint, uneven texture. From your close-up perspective, the surface looks fairly smooth, but if you could step back and see the entire balloon, you might notice vast, continent-sized swells and valleys in the rubber. Our observable universe is just a tiny patch on that balloon's surface. The dark flow could be the gravitational tug from one of those immense super-horizon density variations, a cosmic mountain or valley so vast we only see its slope, the gentle but persistent pull it exerts on everything within our sight. This idea is profound because it suggests the flow is not a pull from a separate universe, but a relic from our own universe's birth, a fingerprint of its uneven infancy written on a scale we were never meant to see directly. This distinction is the key to understanding why dark flow is so unsettling. Our universe is already in motion, expanding in what cosmologists call the Hubble flow. This is the grand, smooth stretching of space itself, carrying galaxies apart like raisins in rising dough. It has no preferred direction, it simply grows outward everywhere at once. Dark flow is something else entirely, a current that moves through that expanding space. To visualize this, picture that classic inflating balloon. Draw dots on its surface to represent galaxies. As you blow air into the balloon, every dot moves away from every other dot. That is the Hubble flow, the expansion. Now take that same expanding balloon and gently tilt it. Suddenly, every single dot also begins to slide sideways all together in the same downward direction. This sliding motion, superimposed on the ongoing expansion, is dark flow. The galaxy clusters are not just being carried apart by the stretching of space, they are also being dragged en masse along a specific cosmic slope. This is what makes the phenomenon so peculiar and so difficult to explain with our standard models. It is not a replacement for expansion, it is a parallel motion, a silent river flowing across the widening landscape of the universe. Detecting this subtle sideways slide against the overwhelming background of expansion is like trying to measure a gentle breeze while standing in the middle of a hurricane, a testament to the incredible precision of our cosmic measurements. Another window into this mystery opened with the searing light of X-rays. While the cosmic microwave background provided a universal backdrop, scientists needed to examine the galaxy clusters themselves more directly. Within the heart of these colossal structures between the galaxies exists a sea of unimaginably hot gas. We are talking about plasma heated to tens of millions of degrees, so energetic it does not glow in visible light but instead emits a torrent of X-rays. Powerful space telescopes like NASA's Chandra X-ray Observatory became essential tools. By staring at these clusters, Chandra could map the distribution and temperature of this intracluster gas with incredible precision. This hot gas is the key to another detection method, a related but distinct phenomenon called the kinetic Sunyaev-Zeldovich effect. Remember, the thermal effect occurs when cosmic microwave background photons get a boost from the hot gas. The kinetic effect is subtler. It arises from the bulk motion of the entire cluster through space. As the cluster moves, the hot gas within it is also moving, and this creates a different, fainter distortion in the cosmic microwave background, a Doppler shift specific to the cluster's velocity. By combining X-ray data, which tells us about the density and temperature of the gas, with the precise cosmic microwave background maps, astronomers can isolate this kinetic signal. It is like having two independent witnesses to the same event. One witness describes the heat of the engine, the other detects its speed. When their testimonies align, the case grows stronger. Several studies using this dual approach have reported detecting the same coherent, high-velocity stream, pointing toward Hydra Centaurus. The X-ray observations provided a crucial, independent line of evidence, suggesting the flow was not an artifact of one particular dataset but a physical reality affecting the cluster's hottest components. Yet, in true cosmic detective fashion, not every investigation reached the same verdict. Some analyses of X-ray cluster data found weaker signals or could not rule out other explanations, adding complex layers to an already tangled story. This scientific push and pull, this ongoing calibration of methods against conflicting results, is not a sign of failure. It is the meticulous process of mapping a shadow, of trying to measure a whisper from the edge of reality with instruments never designed for such a task. The heart of this cosmic argument lies in a process as delicate as restoring a masterpiece. To see the pristine light of the cosmic microwave background, scientists must first remove the glare of everything in front of it. Our own Milky Way galaxy is the brightest offender, a swirling foreground of starlight, dust, and synchrotron radiation that drowns out the ancient whisper. Astronomers create intricate masks and models to digitally subtract this galactic foreground, a painstaking cleaning of the data. It is here, in this subtraction, that critics believe the ghost of dark flow might have been conjured. The concern is that our models of the Milky Way are imperfect. If we subtract a little too much light from one part of the sky, or a little too little from another, we can inadvertently create artificial patterns in the remaining cosmic microwave background map. Specifically, an imperfect subtraction could generate a false dipole, a pattern where one half of the sky appears slightly warmer and the other slightly cooler. This exact kind of dipole is the primary signature of a bulk flow like dark flow. So the million-dollar question becomes, is the signal a real motion of galaxy clusters, or is it a persistent smudge we failed to wipe clean from our cosmic lens? This technical debate is not about negligence, it is about the extreme limits of precision. We are trying to isolate a signal 1 part in 100,000 from a sea of brighter, closer emissions. A discrepancy in our galactic model smaller than the errors in our best maps could theoretically produce the entire effect. Proponents of dark flow counter that they have used multiple independent methods for foreground subtraction, and the signal persists. They argue that if it were merely a cleaning artifact, it would not align so consistently with the motions of galaxy clusters measured by other techniques, like the X-ray analyzers. Yet the doubt lingers, a shadow of uncertainty cast by our own celestial backyard. This is the central battleground, a conflict fought not with telescopes but with algorithms and statistical confidence, where the greatest obstacle to seeing beyond our universe might be our incomplete understanding of our own galaxy. The debate hinges on a different interpretation of that very same light. Some cosmologists argue the entire dark flow signal is not a mystery at all, but a natural consequence of the kinetic Sunyaev-Zeldovich effect from motions we already understand. Their reasoning is elegant and conservative. They propose that the massive galaxy clusters are indeed moving, but not from a ghostly pull beyond our horizon. Instead, their motion is driven by the combined gravitational tug of all the other colossal structures within our observable universe, the known superclusters, the immense filaments of dark matter, the vast cosmic voids. This is the standard model of cosmic structure, where matter clumps together under gravity, creating flows and currents on scales of hundreds of millions of light years. Proponents of this view build sophisticated computer simulations of the universe, virtual cosmos that obey our established laws of physics and contain all the matter we can account for. In these digital universes, they watch the simulated galaxy clusters move. They then calculate what the kinetic Sunyaev-Zeldovich effect from those simulated motions would look like in a hypothetical cosmic microwave background map. The crucial claim is this: when they compare their simulated signal to the actual Planck satellite data, they find a remarkable match. The pattern, the direction, even a significant portion of the speed, can be reproduced without adding any unknown external forces. It is a powerful argument for simplicity. Why invent a cosmic neighbor or a pre-inflationary wrinkle if the existing furniture of our universe, arranged by gravity alone, can create the same shadow on the wall? This explanation paints dark flow not as a revolution, but as a refinement, a testament to the complex, swirling dynamics of the cosmic web we are still learning to map. It suggests the universe is lumpier and its currents more powerful on large scales than we previously appreciated, but still entirely contained within the realm of known physics. The pull, in this view, comes not from outside, but from the collective weight of everything we see around us, a gravitational chorus whose full strength we are only now beginning to hear. The name itself is a masterstroke of cosmic branding. When Alexander Kashlinsky and his colleagues first published their staggering findings, they did not title their paper with a dry technical term. They called it dark flow. This was a deliberate and powerful choice. In science, naming is never neutral. It frames how we perceive a discovery. They could have used the existing jargon, bulk flow, which accurately describes a large-scale coherent motion of matter. But that phrase feels clinical, belonging to the pages of an academic journal. Dark flow, by contrast, instantly connects to the two greatest mysteries of modern cosmology: dark matter and dark energy. It borrows their aura of the unknown. Just as dark matter is an unseen mass shaping galaxies, and dark energy is an unseen force accelerating the universe, dark flow suggests an unseen current directing its motion. The word dark here does not mean evil or empty. It signifies a profound ignorance, a placeholder for a force we can detect only by its shadowy effects. This single, evocative name transformed a complex statistical anomaly into a tangible cosmic character. It invites the public into the mystery, offering a handle on an idea that is otherwise abstract and numerically immense. We instinctively understand a flow, a river, a current. Prefixing it with dark imbues it with a sense of scale and secrecy, hinting that this is not just another piece of the puzzle, but a fundamental force operating from the shadows. The name does more than describe, it captivates, ensuring the phenomenon sticks in the mind long after the details of velocity dispersions or multipole vectors fade. It acknowledges that we are not just measuring data, we are tracking the ghostly hand of something truly beyond our ken. Such a cosmic current would force us to rewrite the universe's opening chapter. Our standard model of cosmology, known as the Lambda CDM model, is a masterpiece of modern physics. It describes a universe born from a hot Big Bang, stretched by a period of inflation, and shaped by the interplay of dark energy, dark matter, and ordinary matter. It is breathtakingly successful, predicting the cosmic microwave background, the distribution of galaxies, and the accelerating expansion with incredible accuracy. But this model assumes the cosmological principle that the universe is smooth and featureless on the largest scales. Dark flow is a glaring directional feature. If it is real and not a measurement fluke, it means our universe's starting conditions were not perfectly uniform. There was a tilt, a whisper of preferred direction baked into the cosmos from its very first moments. This would be like discovering that the foundation of a skyscraper was not level, but ever so slightly slanted. The entire structure built upon it, while still standing, would need a radical reassessment of its underlying stability. Cosmologists would be forced to ask what process in the infant universe could have created such a lasting, immense asymmetry. The answer might lie in a modification to inflation itself, suggesting that inflationary expansion was not perfectly isotropic, but had a slight directional preference, stretching space more in one direction than in others. This single idea unravels a century of foundational assumptions, opening the door to a far richer and more complex cosmic birth than we ever envisioned. The universe is not just a collection of bright things, but also defined by its profound emptiness. Among the largest structures we can map are supervoids, staggering regions of space hundreds of millions of light years across that contain almost no galaxies, just a sparse scattering of dim dwarfs. These are not simple holes, but cosmic deserts of mind-boggling scale. Their emptiness itself might hold a clue to the dark flow. A fascinating hypothesis suggests these voids could create a kind of repulsive gravity, not through some new force, but through a subtle, well-established cosmic process called the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels through the evolving universe, it gains or loses a tiny amount of energy when passing through regions where gravitational potentials are changing over cosmic time. Think of a photon, a particle of light rolling across the landscape of space-time. If it rolls into a deepening gravitational well like a cluster of galaxies, it must climb out, losing energy and becoming slightly cooler. Conversely, if it crosses a region like a supervoid that is becoming emptier and shallower over time, it actually gains a bit of energy, emerging slightly warmer. This effect is minute, but across the vast expanse of a supervoid, it can add up. Theoretically, if there were an exceptionally large supervoid aligned with the dark flow direction, the cumulative energy gain for photons passing through it could create a temperature pattern in the cosmic microwave background that mimics the signature of a bulk flow. It would not be a true gravitational pull from outside, but a mirage created by the repulsive effect of an immense, growing nothingness. Researchers have scoured the sky in the direction of Hydra Centaurus, searching for a supervoid colossal enough to be the culprit. They have found some large voids, but the results are deeply inconclusive. The known supervoids in that corridor, while enormous, do not seem to possess the precise size, shape, or alignment to fully account for the strength and coherence of the observed flow. It is like finding a large valley where we expected a continent-spanning canyon. The void hypothesis remains intriguing, a reminder that the architecture of emptiness can shape the light of the cosmos, but it has not yet solved the mystery. The search continues, probing ever deeper into that dark sector of the sky, wondering if the answer lies not in what is pulling us, but in what is not there at all. This ghostly attractor, if real, would betray its presence by warping the very fabric of space around it. The key to finding it may lie in a phenomenon called gravitational lensing, a prediction of Einstein's theory where massive objects act like cosmic magnifying glasses. When light from a distant galaxy travels past a huge concentration of mass, the gravity of that mass bends the light's path, distorting the galaxy's image into faint arcs or smears. We see this dramatic effect with massive foreground galaxy clusters, but for an attractor beyond our horizon, the lensing would be far more subtle, a vast and gentle warping spread over an enormous patch of sky. This is known as weak gravitational lensing. If a titanic structure in the direction of Hydra Centaurus is pulling thousands of clusters toward it, that same structure should also be gently shearing the images of millions of galaxies that lie even farther away in the distant background. The effect would be incredibly faint, like detecting the bend in a light beam after it passes through a perfectly clean window. But it would leave a statistical fingerprint, a preferred alignment in the shapes of those background galaxies, all subtly stretched in a pattern pointing toward the hidden mass. This offers a direct, if immensely challenging, way to hunt for the attractor. Instead of looking for its light, which cannot reach us, we would look for its shadow, the distortion it imprints on the light of the universe behind it. Future sky surveys, like those planned with the Vera C, Rubin Observatory and the Euclid Space Telescope, are designed to map the shapes of billions of galaxies with unprecedented precision. By analyzing these colossal maps, astronomers could search for a coherent weak lensing signal precisely aligned with the dark flow direction. Finding such a pattern would be a game-changing confirmation, transforming the flow from a statistical anomaly in cluster motions into a tangible dent in space-time itself, a signature of the invisible hand that guides the cosmos. The image is a cosmic river of staggering proportions. Picture not a stream of water, but a current of space itself, carrying thousands of galaxy clusters like leaves, all drifting in the same inexorable direction. This is the essence of dark flow. On Earth, rivers are simple. They flow downhill, pulled by gravity toward a common destination, the sea. The water has no conscious choice. Each molecule follows the path of least resistance carved by the landscape. Now scale that vision up to a universal level. Each galaxy cluster, an island of 1 trillion stars, is like one of those leaves. Their individual motions, their local orbits and dances, are the small eddies and swirls on the surface. But beneath it all is a deeper, more powerful current, a universal riverbed of gravity that guides them all toward a single, unknown terminus. This river is not made of water, but of distorted space-time, and its banks are defined by a gravitational slope we cannot see. The haunting question this analogy forces upon us is profound. Every earthly river has an ocean. So what, in the grand architecture of reality, is the cosmic ocean toward which this universal river flows? What unimaginable basin of gravity could possibly serve as the destination for a current that contains thousands of the universe's most massive structures? The answer lies hidden in the darkness, a pull so fundamental it suggests the entire observable cosmos might be tilting toward a shore we have not yet dreamed of. The Planck satellite's final, most refined data delivered a verdict of profound ambiguity. Some teams, using their own meticulous methods to peel away the Milky Way's glare, analyzed the cleaned cosmic microwave background and found the signal had vanished. For them, the story was clear. The supposed dark flow was a persistent ghost, an artifact of incomplete foreground subtraction that dissolved under the most rigorous scrutiny. In their view, the remaining motions of galaxy clusters were exactly what the standard model predicted: gentle currents generated by the gravitational pull of nearby superclusters and voids, with no need for a phantom attractor from beyond. This was not a failure of observation, but a triumph of precision, demonstrating how easily our own cosmic backyard can cast a misleading shadow. The scientific method thrives on this very tension. When two groups, both armed with the same exquisite data from the most advanced instrument ever launched, arrive at starkly different conclusions, it signals something extraordinary. It means we are pushing at the very limits of our measurement capabilities, dancing on the edge of what our technology and our theories can discern. This disagreement is not a weakness, it is the engine of discovery. It forces every assumption to be questioned, every algorithm to be tested, and every result to be viewed with healthy skepticism. The mystery of dark flow remains unresolved not because scientists have given up, but because the evidence compels them to keep looking, to design even better tests, and to remain humbly open to the possibility that the universe is still hiding its deepest secrets just beyond the reach of our current sight. The sheer distance involved in this mystery is what makes it so difficult to grasp. We are not talking about a local drift, but a current measured across gigaparsecs. A single gigaparsec is a unit of cosmic distance so vast it numbs the mind, representing 1 billion parsecs, or roughly 3.26 billion light-years. The dark flow signal is detected across a volume spanning 2 to 3 of these gigaparsecs, meaning we are observing coordinated motion across a bubble of space over 9 billion light-years wide. To comprehend this, we must attempt a mental journey, begin with our pale blue dot, Earth, zoom out to see our solar system, a tiny arrangement of planets orbiting a single star. Keep going, and our entire Milky Way galaxy becomes a mere swirl of light, one among hundreds of billions. Pull back further, and our galaxy becomes just one member of the local group, a small galactic neighborhood. Continue the retreat, and the local group itself is but a speck within the vast, web-like Virgo supercluster. Now push past that. You must zoom out until dozens, then hundreds of superclusters, each containing thousands of galaxy groups, all come into view. You are now looking at a significant fraction of the entire observable universe. Within this colossal volume, a sphere of space nearly 10 billion light-years in diameter, thousands of the most massive structures we can see are all streaming in the same direction. It is not a flow within the universe, it is the universe itself, or at least a colossal portion of it, exhibiting a silent, unified drift. This scale defies everyday analogy. It is as if every continent on Earth, every mountain range and ocean basin, were all sliding steadily eastward, not from tectonic shifts below, but from a pull originating somewhere beyond the planet's atmosphere. That is the staggering, humbling scale of the enigma, a whisper of motion written across the breadth of creation. This fundamental question haunts every extraordinary discovery. Could the entire phenomenon of dark flow be nothing more than a grand cosmic coincidence, a statistical mirage shimmering in the vast desert of data? This is the challenge of the look elsewhere effect, a subtle but powerful pitfall in scientific analysis. When you search through an immense dataset, testing for patterns across countless directions and scales, you dramatically increase your chances of finding something unusual purely by random chance. It is like searching for a specific face in a crowd of millions. Eventually, you will find someone who resembles your target, even if they are no relation at all. In cosmology, this is compounded by cosmic variance, the idea that our observable universe might just be one unique sample of a much larger reality. Perhaps we simply live in a region where galaxy clusters, by random chance, happen to be moving in a slightly coherent way, giving the illusion of a dark flow, while the universe as a whole remains perfectly uniform. To combat these illusions, scientists wield a powerful statistical tool, the sigma value. This number quantifies how likely a signal is to be random noise. A discovery reaching 5 sigma, for instance, means there is only about a 1 in 3.5 million chance the result is a fluke, the gold standard for a confirmed finding in particle physics. The teams analyzing dark flow have reported sigma values that are significant, often hovering around 3 sigma, which indicates a less than 1% probability of being random. But in a field where foundational principles are at stake, that remaining sliver of doubt is monumental. It is the difference between seeing a shape in the clouds and mapping a new continent. The debate continues not because the statistics are weak, but because the implications are so immense that even a tiny chance of error demands relentless scrutiny, forcing us to ask if we are witnessing a law of nature or a fleeting trick of the light. The resolution of this cosmic argument may finally arrive with a new generation of eyes on the sky. Two monumental projects, now moving from blueprint to reality, are poised to transform our view of the universe and deliver a definitive verdict on dark flow. The first is the Vera C. Rubin Observatory in Chile, a facility with a mirror over 8 meters wide and the world's largest digital camera. Its core mission is the Legacy Survey of Space and Time, a 10-year, deep scan of the southern sky that will catalog tens of billions of galaxies, stars, and solar system objects. It will not take a single snapshot, but a cinematic record of the cosmos, imaging the entire visible sky every few nights. This relentless observation will allow scientists to measure something previously impossible on such a scale: the proper motion of galaxies. While galaxies are so distant their sideways drift is minuscule, over a decade the Rubin Observatory's exquisite precision should detect these tiny shifts. If dark flow is real, the observatory will see not just random motions, but a subtle, coherent drift of countless galaxies, all pointing toward that same patch of sky near Hydra and Centaurus. Simultaneously, the European Space Agency's Euclid Space Telescope is conducting its own epic survey from a vantage point beyond Earth's distorting atmosphere. Euclid specializes in measuring the shapes and redshifts of galaxies with phenomenal accuracy. Redshift tells us how fast a galaxy is moving away from us due to cosmic expansion, but precise measurements can also reveal tiny deviations from that smooth expansion, the fingerprints of gravitational pulls like dark flow. Crucially, both instruments will provide a dataset orders of magnitude larger and cleaner than anything before. They will map the cosmic web in stunning detail, allowing scientists to meticulously subtract the gravitational influence of all known superclusters and voids. If a coherent flow persists after accounting for every last bit of visible and dark matter in the observable universe, the case for an external source becomes overwhelming. Conversely, if the flow disappears into the noise of this superior map, the mystery will likely be laid to rest as a complex artifact of our earlier, limited view. These telescopes are not just upgrades, they are our first instruments truly capable of seeing the subtle currents in the cosmic ocean, and they are pointing their gaze directly at the heart of the darkness. The most breathtaking explanation for this pull lies beyond our universe entirely. Our cosmos might not be the only one. This is the realm of the multiverse hypothesis, a speculative but deeply compelling idea born from the mathematics of cosmic inflation and string theory. Picture our entire observable universe not as everything that exists, but as a single bubble of space-time that inflated after the Big Bang. In this view, the greater reality, the multiverse, is a frothing, eternal sea where countless other bubble universes are constantly budding into existence, each with its own distinct laws of physics, dimensions, and perhaps even different types of matter. They exist in a higher dimensional landscape we cannot perceive. Now, imagine two of these cosmic bubbles floating relatively close to one another in that vast, unseen sea. If a neighboring universe happened to form with an incredibly dense concentration of mass and energy, its gravitational field would not be confined by its own bubble's walls. Gravity, according to our best theories, can leak across the boundaries between universes. The immense gravitational pull from that neighboring bubble could reach into our own cosmos, tugging at everything within it. This would not be a structure within our universe, but an entire other universe acting as the ultimate gravitational attractor. The dark flow in this stunning scenario becomes our first possible evidence of a cosmic neighbor, a ghostly handshake from a reality entirely separate from our own. It offers a tantalizing, almost philosophical hint that our story is but one chapter in an infinitely grander book of existence. The universe seems to be whispering the same secret in two different ways. Beyond the dark flow, another profound anomaly haunts the maps of the cosmic microwave background, a pattern so unsettling it earned the dramatic nickname, the axis of evil. This is not a malevolent force, but a statistical shock. When scientists decompose the faint temperature variations of the Big Bang's afterglow into mathematical components called multipoles, they expect a random, featureless distribution like static on an old television screen. Instead, the largest, smoothest patterns, the quadrupole and octupole, display a strange and unexpected alignment. Their hot and cold spots seem to line up with each other, and even more bizarrely, this alignment points roughly toward the same general region of space as the dark flow, toward the constellations Virgo and Hydra. It is as if the universe's oldest light and its largest moving structures are both subtly tilted toward the same corner of the cosmos. This coincidence is too striking to ignore. Both anomalies independently suggest a preferred direction, a cosmic grain that violates the foundational assumption of isotropy, the idea that the universe looks the same in every direction. The axis of evil imprints a directionality onto the infant universe's first light, while dark flow shows that same directionality governing the motion of mature galaxy clusters billions of years later. This raises a chilling and thrilling possibility. Are these two separate statistical flukes, two independent cracks in our model? Or are they, in fact, two symptoms of the same underlying cosmic irregularity? A fundamental tilt or asymmetry baked into the fabric of reality at its birth. If they are connected, it means the universe was born with a whisper of direction, a faint fingerprint that has guided the flow of matter ever since, from the first flickers of light to the grand march of galaxy clusters. This would not be a minor correction to our story, but a complete reorientation of how we see our place in the cosmos. Our minds are wired for connection, constantly stitching together meaning from the chaos around us. This deep-seated human instinct to find patterns is the silent partner in every scientific discovery, and it casts a fascinating shadow over the dark flow debate. We see faces in the moon, animals in the constellations, and we connect dots to form constellations of understanding. It is a survival trait that built civilizations and launched us into the stars. Yet this same brilliant capacity has a twin, a form of cognitive bias called apophenia, the tendency to perceive meaningful connections in random or meaningless data. It is why we see a rabbit in the clouds or hear hidden messages in a song played backward. In the realm of cosmology, where we stare into the statistical noise of the universe's faintest signals, this line between profound discovery and profound illusion becomes dangerously thin. Are the aligned motions of galaxy clusters a genuine cosmic river, a law of physics written across gigaparsecs? Or are we, the pattern-seeking observers, like sailors lost at sea, mistaking a chance alignment of waves for a current leading to a phantom shore? The data from Planck and other instruments is not a clear photograph. It is a granular, noisy map that requires immense statistical processing to interpret. Scientists must apply complex filters and models to tease out a signal, and at every step, the human desire for a clean, compelling story whispers in the background. This meta-fact does not discredit the search, it elevates it. It means the pursuit of dark flow is not just a technical challenge, but a profound exercise in scientific humility. It forces researchers to build guardrails against their own imaginations, to test their results against the null hypothesis of pure randomness with ruthless rigor. The greatest discoveries often lie just beyond the point where our pattern-seeking brains would naturally invent an answer, waiting for the courage to accept that the universe might be stranger or simpler than the stories we are so desperate to tell. The relentless search for this phantom current has, in a beautiful twist, given us a clearer picture of our own cosmic neighborhood. To test for dark flow, scientists needed an impeccable roster of suspects, a census of the universe's most massive structures. This demand for precision catalyzed a monumental side quest in astronomy, the creation of vastly improved catalogs of galaxy clusters. Projects like the Planck satellite's own cluster catalog were not just byproducts, they became essential tools, meticulously compiled to identify the thousands of clusters needed for the kinetic Sunyaev-Zeldovich analysis. Each entry in such a catalog is not just a dot on a map, it is a data-rich profile listing a cluster's position, its distance, the temperature of its hot gas, and an estimate of its total mass, including the vast halo of dark matter that holds it together. Before the dark flow debate, many cluster catalogs were smaller, less uniform, or focused on specific patches of sky. The hypothesis forced a more systematic, all-sky approach. It spurred the cross-referencing of data from multiple eyes on the cosmos, from the X-ray vision of Chandra and XMM Newton, which see the searing intracluster plasma, to the optical surveys that count the member galaxies, and the microwave sensitivity of Planck itself, which detects the cluster's shadows on the ancient background light. This multi-wavelength vetting process weeded out false positives, like chance alignments of galaxies, and ensured each catalogued cluster was a genuine, colossal gravitational entity. The result is a far more detailed and reliable three-dimensional atlas of the universe's largest building blocks than we ever had before. Even if dark flow ultimately fades into statistical noise, this legacy remains, a sharper map of the cosmic web that benefits every field of cosmology, from studying dark energy's effect on structure formation to understanding how the most massive clusters evolve over billions of years. The hunt for a ghost, it seems, has helped us see the architecture of the visible universe with stunning new clarity. But the strangeness deepens with a fact that defies our basic intuition about gravity. The speed of this cosmic current may not fade as we look deeper into space. In fact, some analyses suggest the bulk flow speed remains constant or could even increase across distances of billions of light years. This is not just unusual, it is profoundly backwards. Think of gravity as a voice shouting across a canyon. The farther away you are, the fainter the shout becomes. Any gravitational pull, whether from a star or a hidden supercluster, should weaken with distance. We expect a flow of galaxies to be strongest near its source and then gradually dissipate, like ripples from a stone thrown into a pond, growing gentler as they spread. Yet the data hints at the opposite. Galaxy clusters 3 billion light-years away appear to be hustling along just as fast, or perhaps even faster, than those closer to us. This turns a cosmic mystery into a cosmic paradox. If the flow is being driven by a single, titanic attractor outside our horizon, its grip should logically loosen on the most distant clusters. For the speed to hold steady or grow across such a vast frontier implies something even more bizarre. Perhaps the source is not a point-like object, but an immense, extended structure, a cosmic slope so vast that even across billions of light-years we are still measuring its steepest gradient. Or it suggests the pull is not weakening because the source itself is moving, or that our understanding of how gravity operates on the scale of the entire universe is incomplete. This constant velocity across the cosmos is like hearing a whisper that does not fade as you walk away, but stays at the same volume no matter how far you travel, a clear signal that the rules of this game are not the ones we thought we knew. The pull of dark flow forces us to question the very nature of gravity itself. For over a century, Einstein's theory of general relativity has been our gold standard, describing gravity not as a force, but as the curvature of space-time by mass and energy. It has passed every test with flying colors, from predicting the bending of starlight to explaining the orbits of binary pulsars. Yet the vast, coherent motion of dark flow presents a challenge on a scale never before examined. Could this anomaly be a sign that our understanding of gravity needs an update on the largest cosmic scales? This question brings us to a fascinating and controversial family of ideas known as modified gravity theories. The most famous of these is modified Newtonian dynamics, proposed in the 1980s as an alternative to dark matter. Suggests that the laws of gravity change in environments of extremely weak acceleration, like the outer fringes of galaxies. In these regions, gravity becomes slightly stronger than Newton or Einstein predict, which could explain why stars orbit galaxies so quickly without needing invisible dark matter halos. But MUND was designed for galaxies. To address the cosmos, scientists have developed relativistic versions, full-fledged theories that attempt to replace or extend general relativity on a universal scale. These theories make specific predictions about how matter should flow and cluster over billions of light years. Some of them naturally generate large-scale bulk flows of matter as a fundamental feature of their equations, flows that could resemble dark flow without requiring any hidden attractors or multiverse neighbors. For proponents, dark flow is not a problem to be explained away, but a potential validation, a piece of evidence that their alternative framework might be pointing in the right direction. The standard model of cosmology, with its dark matter and dark energy, also predicts flows, but they are generated by the gravitational pull of visible and dark structures. The key difference lies in the strength and coherence of those flows. If future observations, perhaps from the Rubin Observatory, confirm that the dark flow is significantly stronger and more uniform than what the standard model's complex web of dark matter can produce, it would be a major point in favor of a modified gravity approach. It would suggest that the strange motion is not being caused by something, but is instead how gravity itself behaves when stretched across the emptiness between superclusters. However, the evidence is a double-edged sword. Critics of modified gravity point out that these theories often struggle to explain other cosmic phenomena that the standard model handles with ease, such as the precise patterns in the cosmic microwave background or the way galaxy clusters collide. Furthermore, if dark flow were to be conclusively linked to a specific external source like a gravitational lensing signature from beyond our horizon, it would actually undermine modified gravity explanations that seek to explain the flow as an intrinsic property of space-time itself. The mystery of dark flow has therefore become an unexpected battleground, a high-stakes test that pits our most successful theory of gravity against its most daring challengers. The outcome could either force a revolutionary rewrite of physics or reinforce Einstein's enduring vision, proving once again that even its strangest implications are written into the fabric of reality. A mystery of this magnitude cannot be contained within scientific journals. Dark flow has surged beyond the world of astrophysics, seeding itself into the fertile ground of our collective imagination. It has become a modern cosmic myth, a narrative springboard for storytellers wrestling with the profound idea that our universe might not be alone. In science fiction novels and films, the concept of an external pull has morphed into breathtaking plots, from entire civilizations fleeing a cosmic tide to ancient, universe-spanning structures guiding galactic evolution. The phrase itself carries a potent, almost poetic weight, suggesting a hidden current in reality that characters can detect, navigate, or fear. It provides a veneer of scientific plausibility to the grandest of tales, allowing authors to ask what might lie in the great beyond without invoking pure magic. This cultural absorption is a testament to the power of a good scientific mystery. Dark flow is not just data, it is a story with a clear protagonist, our entire cosmos, and an unseen, enigmatic antagonist whose motives and nature are completely unknown. It taps directly into fundamental human wonder and a touch of cosmic dread. the thrilling sense that the map of reality has edges and something might be moving just beyond them. By translating complex microwave background analyses into the visceral image of a universal river, science communicators and creators have transformed an abstruse statistical anomaly into a shared cultural touchstone. This journey from sigma values to sci-fi showcases how the most cutting-edge cosmology, when it grapples with truly fundamental questions, stops being a niche academic pursuit and becomes a thrilling part of how we all ponder our place in existence. The sideways drift of a galaxy is almost impossible to see directly. This proper motion, the tiny shift across our line of sight, is drowned by the universe's grander movements. Nearby stars in our own galaxy show this drift over years or decades, a crawl we can measure. But a galaxy millions or billions of light years away is a different story. Its proper motion is so minuscule it would be like trying to measure a snail's progress across a continent while standing on the moon. The primary motion we see for distant galaxies is redshift, the stretching of light as space itself expands, carrying them away from us. Detecting any sideways component against that overwhelming backdrop requires a tool of extraordinary subtlety. This is why scientists rely so heavily on the kinetic Sunyaev-Zeldovich effect. They cannot watch a galaxy cluster creep across the sky over a human lifetime. Instead, they measure the faint shadow it casts on the ancient cosmic background radiation, a shadow that is ever so slightly distorted by the cluster's bulk velocity through space. Imagine standing on a beach watching a massive ship far out on the horizon. You cannot directly perceive its slow, sideways drift, but if you could see the heat shimmer rising from the ocean behind it and observe how that shimmer is warped and stretched by the ship's passage through the air, you could deduce its direction and speed. The hot gas in a galaxy cluster is like that heat shimmer, and the cosmic microwave background is the still, cool ocean behind it. By measuring the precise distortion in that primordial light, astronomers infer a motion too small for any telescope to catch directly, listening for the whisper of a universal current in the silence of ancient light. Decades of analysis have yielded no final verdict. The field of cosmology remains sharply divided over dark flow, a testament to the raw, living edge of scientific inquiry. Respected research teams, all working with the same exquisite data from satellites like Planck, continue to publish papers that reach diametrically opposed conclusions. One group's meticulous analysis reveals a clear, coherent signal pointing toward Hydra Centaurus, a ghostly current flowing through the cosmos. Another team, applying equally rigorous methods to the very same datasets, finds the signal vanishes into statistical noise, attributing any residual motion to the known gravitational tugs of superclusters and voids within our observable universe. This is not a sign of failure or confusion, but rather the hallmark of a profound and healthy scientific frontier. A mystery of this magnitude, one that challenges foundational principles, is not solved quietly in a back room. It is fought over publicly and passionately in the pages of academic journals and at major conferences. Each new paper is a salvo, a fresh interpretation of the data that either strengthens the case for an external pull or meticulously dismantles it. The lack of consensus is not a problem to be lamented, but a process to be celebrated. It means the question is alive, that the evidence is compelling enough to warrant this intense struggle, but not yet definitive enough to force a surrender. This ongoing battle with data and theory is how science grapples with the truly unknown, refining its tools and sharpening its questions against the hard stone of reality. The story of dark flow is not a closed book gathering dust on a shelf. It is a vibrant, unfolding debate where the next observation, the next simulation, could tip the scales forever. Gravity writes its story in motion, and dark flow is not its only sentence. Our cosmic neighborhood is alive with quieter, understandable currents. Our own Milky Way, along with the entire local group of galaxies, is drifting at about 600 kilometers per second toward the massive Virgo cluster, a mere 55 million light-years away. This is a local gravitational pull, a river within our galactic supercluster. On a slightly grander scale, we are also part of a broader journey toward the Great Attractor, a gravitational anomaly hidden behind the plane of our galaxy, some 250 million light-years distant. These are the flows we can explain, the predictable results of known concentrations of mass within the observable cosmic web. They are like the swirling eddies and gentle streams within a vast, expanding ocean. Dark flow is something else entirely. It is not a tributary within the ocean, but the suggestion that the entire ocean itself is tilting. It represents the largest and most mysterious member of this family of cosmic currents, a flow that does not diminish with distance but seems to hold its power across billions of light-years. While the other motions point to structures we can see or infer within our map, dark flow's arrow points stubbornly off the edge of the chart, extending the concept of a cosmic current into the realm of the truly unknown and fundamentally challenging what we believe about the universe's structure and origins. A universe with a preferred direction is a universe with a profound tilt. For centuries, since we cast off the idea of an Earth-centered cosmos, science has guided us toward a humbling view, the principle of mediocrity. It suggests there is nothing special or central about our location, that we inhabit an ordinary region of a vast, uniform expanse. This view is the bedrock of modern cosmology, allowing us to extrapolate the laws of physics everywhere. But dark flow, if real, whispers a different story. It suggests our entire observable cosmos might not be a random, representative sample, but a unique parcel of reality caught in a grand, asymmetric flow. We would not be at the center, but we might be in a special place, a moving part of a structure far grander than we can see. This challenges a core tenet of how we do science, the assumption that what we see here is true everywhere. It resurrects ancient philosophical tremors about purpose and place, not by putting us back in a physical center, but by suggesting the cosmos itself has an architecture with a grain, a texture, a slope, and we are sliding down it. Are we mere passengers on a raft drifting on a perfectly placid lake, or are we caught in a current that flows toward a destination we cannot fathom? The answer reshapes not just our maps, but our very story of existence. The ultimate truth of this cosmic river will be written in data, vast oceans of it. After all, the debate is not about ideas, but about signals buried in noise, whispers fighting to be heard over the roar of our own galaxy. The current stalemate between those who see a profound current and those who see a data artifact is a direct call for a new generation of instruments, tools with the precision to finally separate the cosmic signal from the human uncertainty. The next great leap is already being built, not in orbit around Earth, but on the ground in one of the most extreme environments on the planet. A project called CMBS-4, which stands for Cosmic Microwave Background Stage 4, is an international collaboration to construct a network of ultra-sensitive telescopes at the South Pole and in the high Chilean desert. These locations offer the thin, dry, stable atmosphere essential for peering into the microwave sky with crystal clarity. CMBS-4 is not just an upgrade, it is a revolution in scale. Its combined instruments will survey the sky with an order of magnitude more sensitivity than even the magnificent Planck satellite, and with far greater resolution. Think of it as moving from a standard-definition television to an 8K ultra-high-definition screen for viewing the infant universe. Every subtle variation, every faint imprint will be mapped with unprecedented fidelity. This deluge of new data is the key to unlocking the mystery. With this exquisite new map, scientists will be able to perform the crucial act of foreground subtraction with a confidence never before possible. They will model and remove the light from our Milky Way galaxy not as a rough estimate, but as a detailed, precise portrait, eliminating the primary source of doubt that has haunted the dark flow debate from the beginning. The faint kinetic Sunyaev Zeldovich shadows cast by moving galaxy clusters will stand out against the pristine cosmic microwave background with stark clarity, or they will vanish entirely, proving themselves to be ghosts of our earlier, imperfect vision. The timeline is tangible, with construction underway and first light expected before the end of this decade. CMBS-4 could deliver the data that settles this argument within the next 10 years. It represents a fundamental truth in cosmology that the path to answering our biggest questions is often paved not just with brilliant theories, but with countless meticulous measurements, a patient listening to the universe until its whispers finally become a clear, undeniable voice. Cosmologists wield digital universes to test reality itself. These are not simple animations, but colossal n-body simulations, some of the most complex calculations ever performed on supercomputers. They begin with the standard recipe of the Lambda CDM model, our best map of reality, seeding a virtual cosmos with dark energy, dark matter, and ordinary matter in the proportions we believe exist. They set the rules by general relativity and the known laws of physics, then let the simulation run, watching as gravity sculpts these initial particles over billions of years of simulated time. The result is a breathtakingly realistic cosmic web, a digital twin of our universe complete with filaments, voids, and galaxy clusters that form in the right places and in the right numbers. Within these virtual realms, scientists can do something impossible in the real world. They can track every single particle. They can measure the exact gravitational pull on any simulated galaxy cluster from every other structure around it. They can calculate the bulk flows, the large-scale currents that should naturally arise from the immense but known gravitational landscape of superclusters and voids. These simulations give us a precise prediction, a baseline for how much coherent motion we should expect to see in a perfectly standard universe without any surprises. When researchers then compare these predicted flows to the observed signal of dark flow, the tension becomes stark. The most sophisticated simulations consistently predict that bulk flows should be relatively modest and, crucially, that they should diminish significantly when measured across distances beyond about 2.5 billion light-years. The universe's known furniture simply cannot generate a strong, coherent current on scales of 3 gigaparsecs. Yet the observations, as reported by teams like Kashlinsky's, suggest a flow that remains strong or even constant across these vast distances. This is the heart of the discrepancy, the gap between what our best models of cosmic structure predict and what some data insists is real. If the observations hold, this gap is not a small error, it is a chasm. It means the gravitational forces at play in our real universe are stronger or more coordinated than anything the sum of all its known parts can produce. This simulation versus reality mismatch is the precise moment where comfortable explanations end and the frontier of new physics begins, pointing a digital finger toward forces or influences that exist outside the code of our current understanding. The universe offers its most profound lessons not in answers, but in enduring questions. Dark flow stands as a monumental lesson in scientific humility, a quiet rebuke to any notion that we have the cosmos figured out. We have built machines that can see the afterglow of creation and map the invisible webs of dark matter, yet this single, coherent drift of galaxy clusters remains stubbornly unexplained. It reminds us that for every mystery we solve, the universe unveils a deeper, more perplexing one. This is not a failure of science, but its very essence. The greatest discoveries begin with the courage to admit we do not know, to stare into the data and accept that our most cherished models might be incomplete. Embracing this uncertainty is not a surrender, it is the fuel for all exploration. It is what drove ancient navigators to sail beyond the horizon and modern physicists to probe the quantum foam. On a personal level, it invites us to find wonder in the unresolved, to see the beauty in questions that have not yet found their answers. Our journey to understand dark flow, whether it ends in a revolutionary new law or fades into a statistical mirage, enriches us simply by the asking. It expands the territory of the possible and teaches us to be comfortable dwelling in the mystery, for that is where the next great revelation always waits. The most exotic possibilities lie not in other universes, but in the very fabric of our own. If the attractor is not a cluster of matter but a flaw in space-time itself, the implications are staggering. Theoretical physics allows for the existence of relics called topological defects, not mistakes, but inevitable features that could have frozen into the cosmos during its rapid, searing birth. As the infant universe expanded and cooled, it underwent dramatic phase transitions akin to water freezing into ice. Just as ice crystals can form with cracks or boundaries between different alignments, these cosmic transitions could have left behind immense, stable imperfections woven into the structure of reality. One such possibility is a cosmic texture, a tangled knot of energy fields of almost unimaginable density. Another is a domain wall, a two-dimensional sheet separating regions of space where fundamental forces settled into different states, a border with the mass of countless galaxies compressed into a single, vast plane. These are not objects in space, but structures of space, defects with gravity so intense they could bend the cosmos around them. A single, vast domain wall lying just beyond our observable horizon, for instance, would exert a uniform gravitational pull on everything on one side of it, creating exactly the kind of smooth, coherent flow we detect. This idea transforms the attractor from a hidden supercluster into a cosmic scar, a remnant of the universe's first moments when the laws of physics themselves were still crystallizing. It is a ghost from a time before atoms, before light, a frozen wrinkle in reality that still tugs at the galaxy's billions of years later, a permanent reminder of a symmetry broken when everything began. This cosmic tug of war between expansion and attraction writes the final chapter. For now, dark energy is winning, accelerating the universe's expansion and stretching the cosmic fabric ever faster. The influence of any external attractor, no matter how immense, is currently a mere whisper against that hurricane. But the universe's story is measured in trillions of years, not billions. On those almost unimaginable timescales, the constants we take for granted may not be so constant. If the source of dark flow is a neighboring universe or a super-horizon structure bound to us by gravity, that bond is permanent. While space between us expands, that gravitational thread, however faint, never truly snaps. It simply stretches, becoming weaker but never reaching zero. Now consider a future so distant that the stars have all died and galaxies have evaporated. In that profound darkness, the relentless acceleration of dark energy could one day slow or even cease as the universe evolves into a different phase. Should that ever happen, gravity would become the dominant voice once more. That faint, ghostly pull from beyond our horizon would no longer be fighting an ever-strengthening headwind. Its patient, unwavering influence, exerted over eons longer than the current age of the cosmos, could begin to gather what remains of our observable universe and draw it slowly, irrevocably, toward a rendezvous with its source. This would not be a collision in a fiery, traditional sense, but a gradual, cosmic coalescence emerging of space-time realms, a gentle confluence of realities after an eternity of separation. The ultimate fate would shift from an endless, cold, and lonely expansion toward a silent, gravitational reunion, a twist in destiny written by a hand we sensed but never saw. Gravity's great mystery has become a global conversation. The search for dark flow's truth is not confined to a single lab or nation. It is a sprawling, international effort, a testament to the fact that the cosmos belongs to all of humanity. The very data fueling this debate is a patchwork quilt stitched together by spacecraft and observatories from around the world. The initial clue came from NASA's a Wilkinson microwave anisotropy probe, an American satellite listening to the universe's oldest light. To peer into the searing hearts of galaxy clusters, scientists turn to another NASA marvel, the Chandra X-ray Observatory, its sharp eyes revealing the hot gas within. The crucial follow-up, the detailed map that deepened the mystery, was delivered by the European Space Agency's Planck satellite, a masterpiece of European engineering. The next chapter will be written by instruments like the European Euclid Space Telescope and the American-led Vera-C. Rubin Observatory in Chile, their surveys designed to scan the heavens with unprecedented depth. This is not a competition but a collaboration. Research papers on the flow are authored by teams with names from universities in the United States, Italy, Japan, and the United Kingdom. Conferences in Paris, Tokyo, and New York hum with the same intense debate, conducted in the universal language of mathematics and physics. When a scientist in Moscow runs a simulation of the cosmic web, she is testing the same fundamental laws as her colleague in California. This global tapestry of inquiry reveals something profound. The desire to understand our place in the universe, to decode its hidden currents and architectures, is a shared human impulse that transcends politics and borders. We are all under the same sky, pulled by the same mysterious tide, and in seeking its source, we are reminded that curiosity is our most common ground. The answer, when it comes, will not belong to one nation, but to all of us, a piece of cosmic knowledge earned by a planet working together. The universe's oldest light carries a whisper of motion within itself. To understand dark flow, we must first decode a specific pattern scientists search for, a signature called a dipole anisotropy. Picture a simple sphere like a globe. Now imagine one hemisphere of that globe glowing slightly warmer or brighter than the other. That is a dipole, a two-pole pattern where a property, like temperature, has a clear gradient from one side to the opposite side. This is not a random splotchiness, it is a smooth, global slope. Our map of the cosmic microwave background, the afterglow of the Big Bang, actually has just such a dipole. One half of the sky appears very slightly warmer, the other half very slightly cooler. But this primary dipole has a known local cause. It is essentially a cosmic speedometer for our own motion. Our entire solar system is sailing through space, orbiting the center of the Milky Way, which itself is moving within the local group. This collective motion, about 600 kilometers per second, creates a Doppler shift in the ancient light. The radiation coming from the direction we are moving toward gets squeezed, appearing slightly hotter or blue-shifted, while the light from behind us gets stretched, appearing slightly cooler or redshifted. It is the same effect that changes the pitch of a siren as an ambulance races past you. This expected dipole is carefully subtracted from the cosmic microwave background maps, like removing the sound of our own engine to hear the distant orchestra. The staggering revelation of dark flow is that after this subtraction, an additional dipole emerges, not in the light itself, but in the motion of the galaxy clusters. When scientists measure the velocities of thousands of these massive structures, they do not find random motions canceling each other out. Instead, they find a coherent pattern, a vast statistical tilt revealing that an overwhelming number of clusters are streaming toward one celestial hemisphere and away from the opposite one. This second dipole is the ghostly fingerprint of the flow. It means these clusters are not just sitting still in the expanding universe, they share a common motion through the cosmic microwave background rest frame. They are all drifting in the same direction, like leaves caught on the surface of a slow, universal river, revealing a current that should not exist. Behind every data point lies a human story of exhilaration and frustration. The journey of dark flow is a testament to this emotional roller coaster, a drama played out in observatories and conference halls, not just in the silent depths of space. For Alexander Kashlinsky and his team, the initial moment of discovery was a pure electric shock of possibility. Staring at the processed data, seeing that impossible, coherent signal emerge from the noise must have been a breathtaking fusion of triumph and terror. They had found something that, if true, would shake cosmology to its core. That first rush of excitement, however, is quickly tempered by the sobering weight of responsibility. Publishing such a revolutionary claim is not a victory lap, it is stepping into an arena. The scientific community, rightly skeptical, responds not with applause, but with a barrage of rigorous, often pointed criticism. The pressure is immense, a constant balancing act between defending your meticulous work and remaining open to the possibility you might be wrong. For years, these researchers stood at the center of a storm, rechecking their calculations, refining their methods, all while facing public doubt from some of the most respected names in their field. This is not a conflict of egos, but the essential, often bruising, process of truth-seeking. Then comes the hope of confirmation, the lifeline offered by new data from instruments like the Planck satellite. The anxious wait for those results, the hope that this superior map would validate their years of effort, is its own unique form of suspense. When the Planck data arrived, it delivered not clarity, but a deeper, more complex mystery, a split verdict that prolonged the debate rather than ending it. This is where persistence meets profound doubt, not just in others, but in oneself. The emotional journey does not end with a eureka, a moment. It cycles through a relentless gauntlet of hope, scrutiny, disappointment, and stubborn determination. This human element, the late nights, the defended theses, the heated conference debates, is the true engine of discovery. It reminds us that science is not a cold, linear march toward truth, but a messy, passionate, and deeply human adventure, driven by the same curiosity that makes us all look up at the stars and wonder what secrets they hold. The integrity of any cosmic whisper depends on the silence of the machine that hears it. Before we can trust a signal from the edge of reality, we must be certain it is not a faint hum from the telescope itself. This is the world of systematic errors or systematics, the hidden gremlins that haunt every measurement in observational cosmology. They are not mistakes, but subtle, persistent biases embedded in the instrument or the data processing that can mimic a real cosmic signal. For a claim as extraordinary as dark flow, the first and most rigorous line of defense is to prove it is not merely a ghost in the machine. Teams working with data from satellites like WMAP and Planck spend years, sometimes the majority of their analysis time, on this very task. They must ask, could a tiny imperfection in the satellite's calibration create a false dipole? Could the shape of the telescope's beam, the patch of sky it sees at any moment, be slightly asymmetrical, leaving a directional imprint that looks like a flow? What about the way the satellite scans the sky, painting its map in long, sweeping arcs? Could that scanning pattern itself introduce a coherent pattern into the final data? These questions are not speculative, they are mandatory. Every instrument has fingerprints. The goal is to know those fingerprints so intimately that you can digitally wipe them clean from the cosmic portrait. Scientists run thousands of simulations, feeding fake data that contains no dark flow through their entire processing pipeline, mimicking every known quirk of the hardware. If those simulations still produce a false flow signal, then the game is up. The detection is an artifact. The teams behind the dark flow findings have published extensive papers dedicated solely to this forensic accounting. They have tested different calibration models, applied alternative methods for removing the Milky Way's glow, and used independent cluster catalogs to cross-check results. The fact that the signal persists across many of these tests is what gives it weight. Yet, critics argue that our map of the instrument's own quirks is still imperfect, that an unknown systematic could be lurking in the complex interplay between the telescope's optics, its detectors, and the algorithms that stitch a universe together from terabytes of raw numbers. This tension is the essence of cutting-edge science, a painstaking excavation where researchers must dig through mountains of potential error just to uncover a few precious grams of possible truth. The mystery of dark flow, therefore, is as much a story of engineering and data processing as it is of cosmology, a reminder that to hear the universe, we must first learn the precise sound of our own listening. Science has a secret language of sound. The vast, silent maps of cosmic data can be translated into auditory experiences, a process called data sonification. This is not just artistic whimsy, it is a powerful tool for discovery, allowing researchers to perceive patterns their eyes might miss. So, what does the dark flow sound like? Imagine taking that subtle dipole map, the one showing a hemisphere of the sky where galaxy clusters stream toward us, and the opposite hemisphere where they stream away. Scientists can assign a specific musical pitch to the speed of the flow in each direction. A higher pitch might represent the faster, inbound rush of clusters in the Hydra Centaurus region, while a lower, deeper tone could signify the slower, outbound motion on the opposite side of the sky. When played as a sequence scanning across the cosmos, you would not hear a random cacophony of notes. Instead, you would hear a distinct, haunting chord progression, a slow, coherent shift from high to low frequencies that sweeps across the celestial sphere. This sonic signature makes the abstract tangible. The statistical tilt becomes a melody, the ghostly current transforms into an audible drift. It allows us to experience the data not as numbers on a graph, but as a sensory impression, a cosmic tone poem that underscores the strange coherence of the signal. This creative approach reveals the human heart of science, reminding us that the quest to understand the universe engages not just our logic, but our innate sense of pattern and harmony, listening for the music hidden in the mathematics of the stars. 2008 marked the detonation, the moment the first paper landed with the force of a shockwave. Alexander Kashlinsky and his team published their analysis of WMAP data, coining the term dark flow and presenting a coherent motion of galaxy clusters at over 600 kilometers per second. The cosmology community erupted. That same year, at major conferences like the American Astronomical Society meeting, the talk was not just of the finding, but of its staggering implications. Could the cosmological principle be wrong? The debate was instant and fierce, played out in lecture halls and across online forums where scientists and enthusiasts alike grappled with the idea. The years that followed were a period of intense scrutiny and refinement. The team published follow-up papers, extending the analysis to more clusters and greater distances, finding the signal not only persisted but seemed to remain strong. Critics, however, were publishing their own rebuttals, pointing to potential systematics and arguing the statistical significance was overstated. The scientific process was a public, messy, and vital tug-of-war. Then came the first major external verdict. In 2013, the European Space Agency released its first full-sky data from the Planck satellite. The cosmology world held its breath. Initial analyses were mixed, with some independent groups claiming confirmation of the bulk flow and others seeing a much weaker signal. The mystery deepened, it did not resolve. The 2015 Planck data release, with even more refined measurements, followed a similar pattern. Teams aligned with the dark flow hypothesis published papers saying the signal was still there in the new data, pointing toward the same patch of sky. Simultaneously, other groups published papers using the very same Planck data to argue the opposite, that any remaining flow was consistent with the gravitational pulls from known superclusters within our horizon. By 2018, with Planck's final legacy data release, the stalemate was formalized. The universe's clearest snapshot had been delivered, and yet two legitimate, rigorous scientific interpretations existed side by side in the literature. Public discussions, from documentaries to popular science articles, reflected this split, often framing it as a classic scientific detective story with an unresolved ending. The timeline from that initial paper to today is not a straight line to an answer. It is a branching tree of inquiry, with each new data release spriting fresh analyses, fresh debates, and fresh simulations. This is how understanding is built in real time, not through sudden eureka moments, but through a slow, collective grinding of theory against observation. where every point on the timeline represents another turn of the wheel, another step closer to a truth that remains, for now, beautifully out of reach. The story of dark flow is a masterclass in the scientific method's most sacred rule. An extraordinary claim must face an extraordinary gauntlet of verification. This is not about proving a single team right or wrong, but about subjecting a cosmic mystery to the most rigorous cross-examination possible. The evidence for this universal current has not come from one telescope or one technique, but from a chorus of independent voices, each listening to the universe in a different language. The first and most profound line of inquiry came from the cosmic microwave background itself, using the kinetic Sunyaev-Zeldovich effect to measure the shadow of motion against the ancient light. This was the original witness. Then came the X-ray astronomers, training instruments like Chandra on the searing plasma within galaxy clusters. Their data provided an independent check, measuring the properties of the hot gas needed to interpret the cosmic microwave background distortions correctly. They were not looking for the flow itself, but their detailed portraits of cluster interiors became essential for calibrating the entire search. Meanwhile, optical and infrared surveys from ground-based telescopes were building the third pillar, meticulously cataloging the galaxy clusters themselves, measuring their distances through redshift, and creating the three-dimensional maps that showed where these massive structures truly were in the vastness of space. Each of these methods, microwave, X-ray, and optical, operates on different physical principles, uses different instruments, and is vulnerable to different types of error. When they point toward the same coherent motion, the case grows compelling. But here is the crucial, beautiful twist. The fact that these independent lines of inquiry sometimes produce conflicting results is not a failure of the process. It is the process working exactly as it should. It reveals the hidden complexity, the subtle systematic errors that might lurk in one dataset but not another. It forces every assumption into the light. A disagreement between an X-ray analysis and a cosmic microwave background study is not a reason to dismiss the mystery. It is a roadmap for deeper investigation, highlighting exactly where our measurements or our models might be falling short. This rigorous, often contentious cross-verification is the engine that drives science from intriguing speculation toward durable truth. It ensures that if dark flow is ever confirmed, it will not be because one team shouted the loudest, but because every independent ear, listening in its own way, finally heard the same undeniable whisper from the dark. The most profound answer might be the simplest one of all. After decades of debate, after countless papers and simulations and the launch of our most advanced telescopes, the mystery of dark flow could simply dissolve. The signal, that ghostly whisper of a universal river, might fade entirely under the cold, clear gaze of superior data from missions like CMBS-4 and the Rubin Observatory. What if, in the end, it was just a persistent mirage, a complex artifact born from the subtle interplay of our own galaxy's light and the intricate statistics of an imperfect map? This is not a disappointing end to the story, but a triumphant validation of how science actually works. Science is not a collection of sacred truths, but a dynamic, self-correcting process. Its greatest strength is its built-in humility, its willingness to let go of even the most beautiful and compelling ideas when the evidence no longer supports them. The relentless investigation of dark flow, regardless of the final verdict, has already been a monumental success. It forced us to build better telescopes, to write more sophisticated algorithms for peeling away foreground light, and to create exquisitely detailed catalogs of galaxy clusters. It pushed our simulations of the cosmic web to new levels of realism, helping us understand the expected flows from known structures with unprecedented precision. Even if the phantom current vanishes, we are left with a far sharper, richer, and more accurate map of our own observable universe. We will have meticulously charted the gravitational landscape within our horizon, understanding its currents and eddies better than ever before. The journey itself expands our knowledge, turning a question mark into a period and clearing the ground for the next great mystery to emerge from the darkness. The true power of dark flow lies not in its answer, but in the profound silence of its question. We have journeyed through 50 staggering facts, from the first detection in the cosmic microwave background to the staggering possibility of a multiversal tug, and we arrived not at a solution but at the precipice. This mystery represents the very frontier of human knowledge, the place on our cosmic map where the familiar coastlines fade and the words, "Here be dragons," are written across the void. It is a reminder, humbling and exhilarating, that the universe is far vaster, stranger, and more mysterious than our most ambitious theories can yet contain. For centuries, we believed the cosmos was a smooth, uniform expanse. Dark flow whispers that it might have a grain, a texture, a silent river flowing toward an unseen ocean. That whisper is more valuable than any quick explanation. It is the spark that ignites our curiosity and drives us to build better telescopes, to run more complex simulations, to peer ever deeper into the darkness. This sense of wonder, this awe in the face of the unresolved, is the true and essential fuel for all scientific exploration. It is what transforms us from passive observers into cosmic detectives, forever listening for the next faint signal from the edge of everything we know. The story does not end here because the universe is still speaking. Our task is to keep listening. We have sailed across a river of stars chasing a ghost. 50 staggering facts have guided us from a faint whisper in the cosmic microwave background to the edge of everything we know. We witnessed the discovery, a coordinated rush of galaxy clusters at impossible speeds, all streaming toward a blank spot on our map. We grappled with the shocking implications, a violation of cosmic uniformity that points to an attractor beyond our horizon, perhaps even another universe. We felt the heat of the fierce scientific debate, the clash between those who see a fundamental current and those who see a grand illusion born from our own galactic glare. And we looked to the future, to the next generation of telescopes that will deliver the final verdict. Yet the true power of this mystery is not in a single answer. Dark flow, whether a profound reality or a persistent mirage, has already achieved something monumental. It has been a powerful catalyst, forcing us to question the smooth, uniform cosmos we thought we understood. It has stretched our models of gravity, our theories of inflation, and our very imagination of what lies beyond the observable. It reminds us that science is not a static monument, but a living conversation, a story we rewrite with every new whisper from the dark. So we leave this journey with the most important question of all, one that now belongs to you. Having traveled from the first light of the Big Bang to the possibility of a multiversal shore, what do you believe is truly out there, tugging at the fabric of our reality? Share your theories in the comments below, and if you hunger for more deep dives into the universe's greatest secrets, subscribe and join us as we continue to listen for the next great whisper from the cosmos.